Hello, welcome to this week's Naked Scientists with me, Chris Smith, and with Ben Valsler.
Hello, and in this week's show, an elastic battery that you can bend and you can even stretch up to 3 times its size, and it will still work. And does anybody want to volunteer for a trip to Mars? A group of private investors are looking for a couple of astronaut wannabes, but younger people need not apply, and we'll find out why very soon.
Wonder how young is. Can I still apply? Plus, how do scientists and engineers work in one of the most challenging places on the planet, and that's Antarctica? We find out how the new Halley 6 station was built there and hear about some of the research it's allowing scientists to do there. Ben.
And if you'd like to get in touch with us here at The Naked Scientists, then email chris@thenakedscientists.com, tweet @nakedscientists, or find us on Facebook.
The Naked Scientists podcast is powered by ukfast.co.uk.
And joining us this week for a look at the science headlines is Laurie Winklis. She's from the National Physical Laboratory in Teddington, London. Peter Rogers is from the Cambridge-based science journal eLife. And Laura Howes is from Chemistry World magazine. And kicking off with a look at clean energy. Laura.
So we're looking at hydrogen power, hydrogen fuel cells, which I've been told as pretty much as long as I can remember that I'll be driving a hydrogen-powered car, but it's never quite happened.
What are the benefits of hydrogen? Why do people regard hydrogen as the fuel of the future?
Well, the biggest benefit of hydrogen is that it's clean burning. So rather than creating carbon dioxide and greenhouse gases, you just combine it with oxygen and it forms water.
Well, that sounds great. What's the problem?
The problem is that hydrogen's also a gas, so it's not very dense. Gases are, by definition, they don't have very many molecules in them. And so there's a bit of a problem, and if you want to put it in your car, how do you put a gas in your car? You either have to have a huge, great big balloon on the top, and that's not really going to work, or you have to create pressurised hydrogen and stick that in your car. And people aren't so fond of pressurised hydrogen.
And I suppose also the infrastructure that we have for delivering fuel around the country, petrol station, forecourts and so on, gas mains and things, they're not set up to deliver hydrogen, are they?
No, absolutely not. Everything that we have is based on having a liquid fuel in our cars. And obviously hydrogen is not liquid, not until you really cool it down or really pressurise it.
We're talking of liquids. What's the solution then?
Well, the solution, so it's a good line, is to use methanol. Methanol is a very simple alcohol. It's got 1 carbon, 3 hydrogens around it, and then an OH group, and that's the OH group that makes it an alcohol. And people have been talking for quite a long time about methanol being a potential what we call a hydrogen carrier, so being the source of hydrogen for your car. But the problem has been that to try and separate the hydrogen has required high temperatures and pressures, so it's not something you really want to be going on in your car while you're driving it along on the road. But a group of German and Italian scientists led by Matthias Beller at the University of Rostock in Germany have been working on a catalyst that's ruthenium-based, so ruthenium is the metal in the middle, that can actually do this trick, but at temperatures lower than 100 degrees centigrade and at ambient pressure.
Ruthenium is also a lot cheaper, isn't it? 100 times cheaper than platinum,
yes.
Which is the other way of doing it. So it's attractive both from a temperature point of view and
from
a low
cost
pressure
point
and
of view,
temperature. Yeah.
There's some really good reasons why you'd want to do this. And one of the other really good reasons why you'd like ruthenium is that this catalyst not only reacts once with methanol to take out some hydrogen and leave what the next thing is formaldehyde, but it then reacts again with the formaldehyde, and then that turns into formic acid, and it turns again to turn into carbon dioxide. So it removes every single hydrogen atom that's in the methanol.
But you said there's some carbon, so there's going to be some carbon dioxide. So that sort of detracts from the green value of the hydrogen because there's still some carbon dioxide coming off.
There is some carbon dioxide coming off, but there are ways that you can capture that. There's a lot of ways of talking about putting it with alkaline and turning it into limestone effectively and pulling it out.
There's been a lot of talk of, instead of doing this, finding better ways to lock that hydrogen up, in particular what are called MOFs, metal organic frameworks, which seem to be ways where, again, at sort of standard pressure, you can store enormous amounts of hydrogen, and that way you don't need this extra stage, you don't need the extra chemistry, you just store it better. Which do you think is actually most likely to be an attractive proposition?
Well, I think there are positives and negatives to both. And obviously, as you talk about MOFs, they're very good at storing because they've got a huge porous structure. So that's where the gas goes and stores. But I think if we're talking about the short-term change into technology, probably by using the infrastructure we already have, that's going to allow us to change over. In the future, MOFs may be better, but it's all about that transitional period.
Is this catalyst ready to go? Could we see this going into fuel cells in cars and things tomorrow, or does it still need some work?
It does still need some work. It's not quite fast enough to really convert the methanol to hydrogen as quickly as you need it to burn it in, well, to put it through the fuel cell in your car that converts it to electricity. But these catalysts are very easily tweaked by adjusting the chemistry around them. So I can't see it necessarily being a problem to adjust it and keep adjusting it and refining it till it gets to that point.
It's just one of those things you think, why did no one think of that before? Well, also this week, Cambridge University researchers have tested out a new way of monitoring the atmosphere. They've been using sensors mounted on a battery-powered, remote-controlled flying vehicle called a hexacopter. Now, this is a bit like a helicopter, except it's got 6 rotors. So we sent Ginny Smith along to see the project team of computer scientists and chemists putting it through its paces.
3, 2, 1.
And we have takeoff.
My name's Andrew Rice. I'm a lecturer here in the computer lab. We've just been flying our hexacopter. Really, this is a small part of some of the things that we do where we basically use sensors and computers to try and measure things about the environment. So with the hexacopter, we were measuring CO2 today, but really the bigger project is just how much information can we collect about the world and how can we use that in useful ways to better understand what's going on.
Where did the idea for using this hexacopter come from?
One of my students was watching YouTube videos of other universities flying hexacopters, and we decided that it would be an interesting thing to experiment with as a measurement platform. So we've done things before, putting sensors onto bicycles or sensors onto vans, so this is just another sort of a platform for us to attach sensors to. And really the interesting questions from a computer science viewpoint is about the control. It's about how to decide where to fly it, what flight path it should take, and what interface you present actually to the scientists to allow them to run their experiments.
And have you had to change it much, or do you just buy this thing off the shelf and fly it?
We bought it in kit form, and my students put it together. We've just been sort of generally experimenting, getting, first of all, some knowledge about flying these things at all, and then starting to get used to the idea about what sort of interfaces we might need when we actually try to control it. So at the moment, it's all pretty much off the shelf, and we use a standard sort of helicopter remote control that people use for flying model aircraft. But over time, what we'll be doing is building more sort of abstract interfaces which the computer can use to fly the device.
I'm Rod Jones. I'm a prof in the Department of Chemistry in Cambridge. We're involved in this project, which is obviously at its very early stages, because we've built, over a number of years now, a large number of chemical sensors, which are really small, really light, and low cost. A lot of the studies we do look at urban air quality. Others look at much harsher environments like volcanoes. And I could imagine the kind of technologies that we looked at today working really quite well in both of those kinds of areas.
At the moment, how do you gather data about the air quality?
Well, at the moment we install networks of sensors really at street level. So we could mount them on lampposts or something like this. And what that gives you is a snapshot of what's happening at the surface, but at lots of different sites. And what this is going to allow us to do, hopefully, is to allow us to extend our knowledge in the vertical, the measurements in the vertical, so that we can see how the structure that we know is present at street level, for example, will extend upwards in altitude. And once we can do that, we hope we can do a much better job of understanding the exposure of individuals to air pollution and then arguably and possibly the health effects that are going to accrue as they're exposed to different levels of pollution.
So the hexacopter we were looking at today is an unmanned vehicle, so you fly it with a remote control. What are the benefits of that compared to, say, putting these sensors on a normal aeroplane or helicopter?
Well, there are quite a few benefits. There's an obvious one, which is cost. These are an awful lot cheaper than flying a manned aeroplane. But there are more relevant ones in some ways, because we can actually take a hexacopter or something like a hexacopter and put it into an environment that we couldn't possibly use a manned aeroplane in, either on the grounds of safety in terms of where the aeroplane is flying very close to the ground, or in terms of, say, a volcanic eruption where we know that there could be damage caused to the aeroplane by the volcanic plume itself. And we could put something like this through a volcanic plume, and there's no risk, personal risk involved. So it's actually much safer science in that way.
And has everything gone pretty smoothly so far, or have you had any problems with flying it?
Well, this is our second one. The first one we were flying and we just attached the GPS chip to it, and we think there was a software bug which caused it to turn itself upside down and fly to the floor. And that caused about £1,000 worth of damage to the hexacopter. So we had to buy another one, basically. But other than that, there's been no sort of major mishaps. No one's been injured, and we always stick to the flight path.
Andy Rice from Cambridge University's Computer Lab, and before him, Rod Jones from the Department of Chemistry, and they were speaking with Ginny Smith. And I did actually chat to Andy Rice about that, and he told me that the energy consumption, the batteries are supplying 60 amps to keep that thing aloft, which is quite some discharge rate. It buys them half an hour of airtime. But the batteries alone must be a lot of the price, I would think. And speaking of batteries, maybe they need a deformable one. Laurie, what's this all about?
Hi, Chris. I saw this really interesting paper in Nature Communications this week, and it's about a stretchy battery. So not just a flexible battery, but a battery that can actually be stretched and increased in size by about 3 times, and it will still work.
Ooh. So, first of all, what sort of battery is it then?
It's actually just lithium based. So these researchers haven't gone back to the drawing board, really. They haven't tried to find a new interesting material. But the genius in their research is actually the interconnects that connect these small discs, so just a couple of millimeters wide, discs of lithium that are interconnected by serpentine, like S-shaped interconnects of copper. And that is actually what gives it its stretchiness. It's based on something called self-similar geometry, which says that if you can imagine, every S-shaped wire is actually made up itself of lots of much smaller S-shapes. So as you pull 2 of these discs of lithium apart, you first unfurl the large S, and as you keep stretching it, you start to unfurl each of the small S's, but without putting any great strain on the actual lithium.
Oh, I see. So the way they've done this is that you've got lots of little tiny batteries. I mean, they're really cells, aren't they, which are the lithium bits, and they don't stretch, but they're connected with wires which, because of that S shape, mean there's an enormous metal reserve in the interconnects. So when you do stretch the material, you're just lengthening or unwinding the wires temporarily.
Yeah, I mean, it kind of seems obvious, really, when you think about it. It's one of these things. Why hasn't someone done it before? Yeah, it's exactly that. They have little tiny islands on their prototype, 100 discs of lithium that are all interconnected with these incredibly stretchy copper interconnects.
How much will it stretch by?
You can actually stretch it by about 3 times its size, so 300%, which is way beyond anything, any other flexible electronic devices that have been produced so far. And they did a really clever thing. They stretched it, they folded it, they twisted it, and they actually stitched it into a jumper on someone's elbow and asked their researcher to bend their elbow up and down and connect it to LEDs. And all the time, the battery kept working.
Now, this group have previously done stretchy circuits, haven't they? So, and using the same sort of technique. So is the idea that these batteries will help power those same stretchy circuits? I know they've worked on patches that can do monitoring stuck to your arm, so you can be monitored for various health benefits. Is that the idea?
Yeah, exactly. So these guys are from Northwestern University. So it's Professor Wang from Northwestern and John Rogers from the University of Illinois. And yeah, they've been developing these stretchy or at least flexible circuits for some time for the health industry. So exactly that, to monitor patients' skin temperature and things like that. And this has been a bit of a bottleneck actually within the flexible electronics market. You can actually already produce displays that can bend and fold without being damaged, but there hasn't really been anything to power them up until now. You've had to basically plug them into the wall. So these guys decided to see if they could fill that gap, a gap that they already were experiencing, by producing this flexible, stretchy battery.
One of the things that we know about metals is that when you repeatedly bend them and then straighten them and then bend them again, then they go through something called fatigue. If these S-shaped bits of wire are just normal metal, are we not going to see this fatigue effect, and actually the lifetime of these batteries will be quite limited?
Yeah, Ben, actually the lifetime is pretty limited. These guys it's actually John Rogers, part of the group. They've characterised this through 20 charge-discharge cycles while stretching it. So 20 cycles is basically about 7 days of operation, and after that they can see the fatigue issues. So the lifetime at the moment is pretty short, but they have some ideas as to how they can lengthen it by improving, maybe even increasing the thickness of some of these interconnects and changing the chemistry, really.
And maybe they'll make them go a bit further at a stretch.
Let's hope so.
Who knows, Laurie? Thank you for that one. Also with us, Peter Rogers from eLife, and it's been a big week for open access, hasn't it? Tell us more.
That's right. The past week or so, we've had a lot of developments in the world of open access. We've had announcements and reports and memoranda from the US Congress, from the White House, from the House of Lords, from the Higher Education Funding Council for England and related bodies.
Just to be clear, open access, this is where people say, I'm publishing some scientific research and it's not going to be locked up behind a paywall on the internet of the journal who are publishing it. It's going to be available to everyone indefinitely for free.
Exactly.
So what's the big deal? Well,
the big deal is that most of the scientific papers in the world at the minute are not open access. They are behind those paywalls, as you described. It's difficult to get a good estimate, but most people agree that something like 15% of the literature is freely available. And the overall philosophy of the open access movement is the vast majority of research is funded by taxpayers. Governments fund research councils and research funding councils with money that ultimately comes from taxpayers, yet when the results of this work is published, the taxpayers cannot see it, and neither can their GPs or charities or small companies. Before the internet, it would have been impossible to make it freely available to everyone because journals were printed and posted, and really you had to go to an academic library to see them. But now all scientists read journals online, and so everyone in theory should be able to read them online as well.
I mean, that sounds very laudable until you think an organisation like the one that Laura works for, the Royal Society of Chemistry, learned societies have journals which traditionally they have relied on as a source of revenue, and they then reinvest that revenue in their membership to fund, say, training for PhD students, conferences, other sorts of grants. And so I could see that there may actually be a negative impact if you damage their revenue stream like that.
Well, there's two types of open access. One is called green and one is called gold. And under the gold model, basically the revenue that you talk about that libraries pay to publishers to buy the journals is replaced by something called article processing charges, where the authors pay. And they treat the publication of the research almost as a cost of research. You do some research, it costs hundreds of thousands of pounds. You pay an extra £1,000 or £2,000 to get it made freely available. So you can, if you think globally, the money at the minute starts with the government, ends up with the publisher going through a particular route, but 85% of the papers cannot be read by people outside those universities. You can have the money start in the same place, end in the same place, and everyone able to read the papers, which has got to be better.
Is there any evidence yet that being open access is good for the researchers? Do we see open access papers cited more in other research, or is it still actually the ones that are behind these paywalls and the prestigious paid-for journals that are the ones that get the citations?
It is true that the journals with the highest impact factors, as a rule, are subscription journals with paywalls. I'm not sure there's what you would call data. There's certainly examples of where journals or papers have been made open access and have been more cited, or the journals have increased their impact factor. But there's nothing sort of definitive in that, I would say.
What about the big publishing groups, the Natures and that kind of thing of this world? How are they reacting to this? What's their take?
Well, it's strange. On Tuesday night, Nature invested and became the largest stakeholder in a very new open access publisher called the Frontiers Group, based in Switzerland. So I think they realise that this is the way the tide is going, and the future hopefully will be open, and that they need to be part of that movement.
Now, given that you are the features editor of eLife, a brand new journal on the block, which is by definition open access because your funding comes from people like the Wellcome Trust, that must be music to your ears then.
Absolutely. It's I think we're sort of, one of the things that eLife wants to do is to try and catalyse change in the publishing industry. So the more journals that become open access, the happier we are.
Thank you, Peter. Well, maybe you'd like to volunteer if it doesn't work out for what Ben's got in mind. They want to send people to Mars, but you can't be young.
Well, they're not looking for somebody young, no spring chicken for this particular mission. They want somebody with, shall we say, a bit of life experience. And actually, they want two people, and in particular, they want a couple, because they have said that mankind's first mission to Mars should be represented by one of each gender. And if we're going to put people in such close confines for such a long time, then we're going to need a married couple.
Who's actually doing this?
So this is a mission by Inspiration Mars, and they are a private, not-for-profit company founded by former space tourist Dennis Tito. You might remember that he spent a considerable amount of his own money.
20 million, wasn't it, to spend 7 days in space?
That's right, on the International Space Station, and he was the first space tourist, and he doesn't actually want to go he doesn't want to go to Mars himself, but...
One has to ask why.
Well, actually, I think he thinks he might be a bit too old. Their company wants to send a manned craft to fly not to Mars, but past Mars. So it wouldn't actually be a landing mission. It wouldn't go into the atmosphere. It would be about 100 miles close and then turn around and come back. And the key thing is that they want to launch as early as 2018.
Fairly close time point, isn't it? Why so soon?
Well, it's only 5 years, and that really is very soon. But the thing is that January 2018 is a really good time to launch this sort of mission. Now, it coincides with the solar minimum, so that's the period when the sun is at its least active, and so there's going to be less of a risk of exposure to radiation. But also, the alignment of the planets is correct for this sort of mission. That may sound like it's based on a horoscope.
A little bit horoscope-esque.
It does, but actually they mean it in terms of the physics. So the alignment happens to be right to make it as quick as possible, so it'll be the fastest mission they could do, but also it would be a free return mission. So even if something goes wrong and they lose power, the actual trajectory will see the craft return to Earth using no fuel. So that should enable us to do what we call a fast, free return mission. So it's probably the safest way we can do this. But of course, this only actually gives us 5 years to make sure that all the technology we need is in place.
I was just going to ask, how long would this journey take? We were talking at lunch at work about this, and we weren't sure we'd necessarily want to be stuck with anyone, however much we loved them, for days and days and days.
Well, yes, it will be about 501 days. That's how long it's calculated to be. But as you're quite right, you wouldn't want to be trapped with somebody that you didn't know you could cope with. And this is why they're looking for a mature couple. They want a couple who their relationship has been proven to stand the test of time and the trials that life can throw at you.
Have we actually got rocket technology that can get people out there and back? Because it's one thing sending a space probe, it's another to have something that people can live in.
The plan is that after launch they will deploy an inflatable living habitat that then actually gets dropped off before we come back into Earth. But the trick is actually the use of this clever physics of this free return that means that we don't need to have the rockets on all the way. So the technology definitely exists to do this round trip, and it's the same sort of physics that they planned for the Apollo missions, for the lunar missions. Has
this been received by the sort of global media and other space experts? Have they laughed, or has this been taken seriously?
I think it's actually been both. I think there's been a lot of people who have said what we have, which is they're looking for old people to send to Mars, which sounds like a bit of fun. But actually, it's quite a serious mission, and it points out what we can learn and what we can gain from having the private sector doing these sorts of events. So already we've had supplies delivered to the International Space Station by the private sector, and now it looks like they're going to be the ones that are pushing us to get people visiting Mars.
Thank you very much, Ben. And thank you also to Peter Rogers, Laura Howes and Laurie Winkliss. And you can find out some more information, including the references to the papers we've been discussing and some background news information on our website at nakedscientists.com/news. This is The Naked Scientists with Ben Valsler and with me, Chris Smith. If you'd like to get in touch with any questions or comments, you can email chris@thenakedscientist.com. You can tweet @nakedscientists, or you can also find us on Facebook.
And it's due to get a bit chilly later on in the show as we discuss the difficulties with building in the Antarctic. But first, in tropical climates, parasitic infections such as malaria are a huge problem, and new drugs need to be continually developed to help fight the disease and keep up with resistance. And now a new screening method for potential drugs has been developed using yeast to help identify effective compounds.
To find out more, we're joined by Dr. Elizabeth Bilsland from the Cambridge Systems Biology Centre. Hello.
Hello.
So, first of all, how do you find anti-parasitic drugs in the first place using traditional methods? What's the usual way of doing this?
Companies like GlaxoSmithKline and Novartis, they cultivate the parasites in the lab, and that is possible for the African malaria, so Plasmodium falciparum, and treat them with loads of different chemicals. So they have hundreds of thousands of different chemical compounds that they treat these parasites with and see what survives and what doesn't. And then for the best candidates, they test against toxicity in human cells.
Yes, I was going to say, it doesn't sound like a quick thing to do, because then you can try it against the parasite, but then you've got to prove that the drug is toxic for the parasite, but safe for the host,
the human. Exactly.
Yes.
Exactly.
So you've got 2 rounds of testing to do for everything.
Yes, and that is the parasites that most of the work is being done, and it's the one that's possible to do the highest throughput with the current methods. But there are several different parasites, like Plasmodium vivax, that cannot be cultivated in the lab or cannot have a full cycle.
This is one of the other strains of malaria, isn't it?
Yes, another strain of malaria that affects South America and Southeast Asia. So it's the most widespread form of malaria. And the biology of that parasite is very different from the African malaria. But you just adapt the drugs from the falciparum malaria to the vivax and hope that it works.
And it may not necessarily be the best solution to the problem.
If, for example, it does not target the liver stages that are the recurrent stages of the vivax malaria.
I see. So what have your group come up with as an alternative which solves a lot of those problems?
We engineer yeast strains where we remove genes that are essential for yeast to survive and replace those with genes that are essential for the Plasmodium to survive, or for the parasite that causes sleeping sickness or Chagas disease or schistosomiasis. And we also did the same, replacing the same gene with a human gene. And the idea is that we can grow the yeast strains in a way, grow them in a tube, treat them with a drug, and see if the yeast with a parasite gene dies, but not the yeast with a human gene.
I see. So you're turning the yeast into a sort of surrogate parasite. So by putting the parasite genes into the yeast and then testing those drugs on the yeast, if the yeast dies off with the parasite gene, that's good. When it's got the human equivalent, it stays safe, that's good. And it means you can do this much more quickly because you're growing yeast, which is easy to grow.
And from the start of the experiment, we have a direct measure of toxicity, so we know that it's not having the possible side effects in humans. We know that the drug goes into the living organism, and we know which target is hitting. Because when you treat the entire parasite, you don't know how the drug is acting at all. So you can't optimize the drug if you don't know what it's hitting.
Is it working? Have you got some compounds out of this that prove this technique does work?
Yes, definitely. In the yeast screen, we selected, for example, 36 compounds that kill the yeast with a Trypanosoma brucei. That's the agent that causes sleeping sickness. So out of these 36 compounds, we tested them in purified parasites in the lab, and we saw that 60% of them actually kill the parasite at 10 micromolar. With the same concentration of drug, if you tested straight in the parasite, you would have about 0.1% of hit rate. So from 0.1% to 60%, I think that it's quite a good improvement. In the cases of parasites that you can cultivate easily in the lab, maybe that's not so important. But with a case of Vivax malaria, that's a South American malaria, if you want to test if the drug is working, you have to be based on the area where that malaria is endemic, extract blood from about 50 patients infected with malaria, purify the parasite, treat that with a drug, and see if it works. So to have 50 sick volunteers for each drug it would really not be realistic. But if you select 15 candidate drugs, then you can start to consider. And that's the stage that we are at the moment. We have some drugs that are in a stage that we're going to take to the lab in Manaus with a collaborator from Brazil.
Wonderful piece of news, given that there are something like 500 million cases of malaria every year and perhaps as many as 1 million deaths. I mean, that's really wonderful news. And also coming in the year when we're celebrating 200 years since the birth of Dr. David Livingstone, who is, of course, the famous missionary who got malaria himself 27 times, I'm told. Thank you very much, Elizabeth. That's Elizabeth Bilsland from Cambridge University, and she published that work this week in the journal Open Biology.
Now, 80 million trees in Britain are at risk of dying from ash dieback. That's a fungal disease that's gradually spreading across the country. But there is a glimmer of hope thanks to scientists at Queen Mary University of London who are decoding the ash tree's genetic sequence to discover how to produce a tree strain that's resistant to the disease. Planet Earth's Richard Hollingham spoke to the scientist leading the research, Richard Buggs, and forestry research manager, Joe Clark.
Well, ash is one of our most important trees. It's the third most common tree and the second most widely planted broadleaf tree. It forms a very important part of many valued ecosystems. A lot of our British biodiversity is dependent on not so much the ash tree itself, but on the structure of a woodland, a broadleaf woodland that's created through different species composition. So ash is very important, and it's a very important timber tree. Ash is quite elastic. It's quite good at absorbing impacts, and it's used quite widely in things like flooring and door frames. Morgan cars are still made from ash trees. It's widely used.
So, Richard, you're starting with the ash trees here, these small ash trees, these young ash trees. What are you actually going to do?
So I'll be collecting a sample here today. I'll be taking that back to my lab at Queen Mary University of London, and my PhD student, Yasmin Zoran, is going to extract the DNA from the bark of that specimen. We'll be sending that DNA sample to Eurofins in Germany, and the data they're going to give back to me is a whole load of short reads from throughout the genome at random, covering the genome 155 times over. And we have to put that all together using high-performance computers to assemble the genome of ash.
And essentially you'll get a list of all the bases in the ash DNA.
Exactly. The ash genome is 950 million bases long, so that's just under a third the size of the human genome. Sequencing a genome is a bit like taking aerial photos of an unexplored island. Just imagine there's an island in the Pacific that hasn't been explored. All we know is how big it is, and we want to know more about it. And so what we might do is send planes over it, taking lots and lots of small aerial photos at random, and then we have to take those little aerial photos that we have, which in our case are reads of DNA, and put them all together in a big jigsaw puzzle to recreate on the computer the whole genome code of the ash tree.
OK, you've got your secateurs in your hand. You're going to take a sample now. So you're actually going to chop off a little bit of
so
this tree here.
Taking a sample here. So
there we go. So you literally take that back, and you've got to do all that work
absolutely. This
on
is
it.
The start of a huge program of research.
So you have the sequence of DNA. How does that help you with looking at which trees are going to be resistant to the disease?
The genes for resistance are not just going to pop out of the genome as soon as we sequence it. We're going to actually have to find them. And the way we do that is to look at lots of trees and find ones that are resistant and ones that are susceptible, and then genotype them. And
so when you say genotype, look at the genetics of them, the sequence of them.
So we won't sequence the whole genome of them, but we'll look at a subset of the genome using a system of markers. Like, for example, there's a system called RAD markers that look at thousands of points across the genome, but not the whole of the genome, but enough of it for us to pick out the genes that are associated with resistance or susceptibility to ash dieback.
The underlying genetics is absolutely of paramount importance, whether you're trying to produce robust populations to combat climate change or, in fact, a novel disease like Chalara. The genetics is what underpins all our research work to produce productive timber trees for the future.
Richard, how long is this going to take?
The sequencing of the genome should take less than a year. Well, we should be releasing a draft assembly of the ash genome very quickly. Technologies have moved on really fast in the last 5 years, and this is now quite a routine thing to do.
And Joe, how soon do you expect to be able to use this information?
Well, as soon as Richard gives us those individuals that are likely to be resistant, we have very good techniques for bulking up material. So ash grafts very, very easily. You can graft it onto a rootstock, and then you can be producing seed perhaps in 5 years' time.
Joe Clark from the Earth Trust and Richard Buggs from Queen Mary University of London on efforts to save the ash tree. And you can find more from Planet Earth online at our website. That's at thenakedscientist.com/Planet Earth.
This is The Naked Scientists with Ben Valsler and with me, Chris Smith.
If you would like to get in touch with any questions or comments, then you can email Chris at thenakedscientists.com, tweet at Naked Scientists, or find us at thenakedscientist.com/Facebook.
Antarctica is one of the most challenging environments on Earth. But despite of this, there's lots of scientific research that needs to take place in Antarctica to help us to understand the world around us. In a little while, we'll be speaking with Tamsin Gray and Jonathan Shanklin, who both research climate and atmospheric science with the British Antarctic Survey. But before that, we're joined by Carl Tuplin, who's the project manager for the British Antarctic Survey's Halley 6 project, and Peter Ayres from ACOM, who were both involved in engineering the project. So let's begin with Carl. So what's actually the vision for Halley 6? What was needed down in Antarctica? What did you want to achieve?
Well, we're going to lose the old station. The ice shelf's going to carve off, so we're going to lose it. So we knew we needed a new one. Exactly where that carving line was going to be is quite difficult to predict.
So you're literally going to have your old station float away on a lump of ice?
Yes, we've actually demolished it and cleared it now, but we would have done, yes. Exactly where the carving line's going to be was difficult to predict, and during the design life of the new station, there's some big chasms behind it, so it's going to make the ice shelf a little bit more unstable. So one of the visions for the new one is it had to be relocatable. We had to be able to move it, because we don't want to be spending huge sums of money again building another station in 10, 20 years' time. So that was one of the visions. A couple of the other factors is we wanted something that was going to be stimulating for the scientists to work in. The previous stations, nice, square, boxy, very good engineering point of view, not necessarily the most stimulating place to live or work. So again, we got architects involved to try and produce a better place to live and to work. Further, there's a lot of effort needed to survive in the Antarctic, a lot of work. Because the main aim is to do the science there, we're trying to reduce the amount of effort to survive, to make it easier to live there.
Were you at the previous station, Tamsin?
Yeah, that's right.
What's it actually like when people just think, oh, I'll nip off down to Antarctica? What's actually involved in being down there? What's it like?
Day-to-day life's quite different from back here, so to get all the water to drink...
It's warmer, you mean? No, I'm just kidding.
Well, it's summer down there right now, but not quite. So, just for washing and showering and things, we had to go outside and shovel snow in a big team for about an hour every day into a hole to melt. Although now with the new station, they've got machines doing a lot of that work for them. So just every day, you walk to work. Sometimes I could fall over 7 times in big snowdrifts because there's a blizzard going on and I could barely see my hand in front of my face. So there's just all sorts of challenges that you wouldn't really think about with life back here.
Have you sorted those challenges out, Carl?
Yes, for instance, on the water side, where it used to be people shoveling snow into what we call a melt tank, to a long shaft down to a big kettle under the ice. Now we have modified shipping containers with large tanks in and heating grills at the bottom, and you can open the doors on the lid of the container and just bulldoze snow in. So it makes it a lot easier and a lot simpler, and you can melt a lot more water.
And then you're spending time doing research, not just
so
shoveling.
You're spending more time. There's less people required to do that sort of work, so you're spending the money on science rather than on the station support.
Peter from ACOM, the engineers behind this project, what's actually involved in building something like this as far away and in those sort of exigent extremes that we get in Antarctica?
Halley 6 is without doubt the most challenging building we have ever been involved in designing. Just starting with the climate in Antarctica, it's incredibly cold. It goes down to minus 56 degrees centigrade on the site, over 100-mile-an-hour winds, 106 days of continuous darkness in the winter. And so just building in cold climates in itself is a very, very challenging thing to do. But Halley was special even by our Antarctic standards. It is the world's first fully relocatable research base. And so we had to design a building that was fleet of foot, if you like, that was able to be moved, but also was robust enough to survive the incredibly challenging environment. And I guess the most challenging thing of all, in fact, was the logistics, the supply chain, how we would bring the materials to Antarctica to build the base.
It's not just any old materials either, is it? Because, I mean, as someone said to me the other day and really made me think, you can't weld metal in Antarctica in the same way as you could just knock a few bits of metal together in a warmer place.
Well, there are lots of things you wouldn't want to do in Antarctica because you're constantly working in sub-zero temperatures. So that means you have to be generally in pretty warm clothes with thick gloves and things like that. So even things like bolting, you want bolts that are big enough that you can handle them with gloves, and you want components that can be clipped together. But probably the most overwhelming constraint of all is that because of the short summer season when people can generally work there in construction, you only have about 12 weeks within which you can actually build anything. And so that would say prefabrication. You would immediately think, let's prefabricate things and just ship them in. But there's another constraint, which is that because the base is built on a floating ice shelf, everything has to be delivered by ship, and it has to be towed across very fragile frozen sea ice. And so that constraint says that you have to limit the size of every component you take to Antarctica. So really the whole design to some degree was dictated by those two key constraints, that on the one hand you want things to be as big and prefabricated as possible. On the other hand, everything has to be small enough to be shipped across the sea ice. And when you put those two constraints together, that's effectively the starting point for how we conceptualise the design.
So Carl, do you say to Peter, this is what we want, and then he says, this is what I can do? I mean, how does it work?
No, it's the other way. It's the other way around, really. This is Halley 6, so we built 5 stations before. For Halley 6, what we wanted was to go out to the marketplace and see what the best of the marketplace could actually do. The engineers, the architects and the construction teams, and see what they could come up with. So what we did, we presented them with the problems, because there's a lot to understand and take in all in one go. So what I actually did was launch a multi-stage design competition, and started that competition by showing the teams the problems of the Antarctic and what they had to overcome, and then said, go away and come up with your ideas of what would you design. Now, we didn't necessarily expect those designs to work, but we wanted to see what ideas are out there to overcome the problems. There were 6 teams did that. Then we narrowed it down to 3 of those teams, the ones we thought had the most potential, the designs that had the most potential to take forward. And we put a BAS team with each one of them. So the BAS team had the Antarctic knowledge, and we put a contractor with each team as well. So you had 3 teams running, and in each team you had the designers, had the design concepts and impetus. You had BAS, who had the Antarctic and the logistics knowledge, and you had the contractor who had the build and the procurement knowledge. And that way we then had 3 designs in the competition running together to try and come up with the best one.
And that was you, Peter. So how did you actually deliver this? What's the process for getting this new station erected in Antarctica? What did you actually do?
Well, as I said before, one of the key things was to prefabricate as much as possible. When we originally turned up on the ice with a great big Russian chartered icebreaker ship, we had steel frames which form the basis of our modular building. So the building is in fact made up of a series of 8 pod buildings, if you like. They're pretty big. They weigh in excess of 100 tons each. Each of them is based on a steel frame which is prefabricated, loaded onto the ship, dropped off on the ice on special skis that are made just for the transit and towed to the site. And from there on, all of the different components are kind of modularised, prefabricated components that, as far as possible, clip together to make the base. So the pods are founded on giant hydraulic legs, which allow the base to climb mechanically out of the snow every year. They're founded on huge skis, which are the same technology of the skis you use on sledges, but much, much bigger, so the buildings can be moved. And then we bring all of the rooms that form the base, are prefabricated modular bedrooms and plant rooms, toilets, etc. Those get loaded on top of the steel frames. And then we developed a very innovative fibre-reinforced plastic composite cladding system, which provided the final resistance to the weather, which was the very well sealed and thermally insulated enclosure to keep everybody safe and sound inside.
Which is good to hear. And dare I ask the price tag?
Are we going to talk about price, Carl?
Yeah.
Yes.
The actual construction contract is just under 26 million, 25.8, 25.9 million.
Actually, I thought it was going to be more.
That's the construction
like that.
contract,
Yeah.
and the total project is touch under 50 million.
Peter's wage bill?
That's add his bonus on and we'll... But yeah, just under 50 million is the total price tag. That's all the logistics and everything to make it happen.
So we just heard that Halley 6 was designed with the scientists in mind to make them as comfortable as possible and enable them to do groundbreaking research. We've already introduced Tamsin Gray and Jonathan Shanklin. Thank you again for joining us. We've heard a little bit about the challenges of day-to-day life, but how is research different under that sort of environment? Tamsin, how do you have to adapt research to cope with those conditions?
Sometimes it's just really simple challenges, like we've already spoken about, working outside, doing fiddly tasks with your hands. You know, one of the tasks I had to do, dead simple, go out and measure 10 metal poles in the snow to see how the accumulation of snow varies from year to year. And sometimes I would have to go back in the middle of the winter to warm my hands up in the middle because I could only measure 5 before they'd frozen. And I won't tell you about the time when I held the metal tape measure to the pole with my mouth for a second whilst I did something with my hands because that didn't end well.
Show us your tongue. It's still there.
It's healed just about. That was about 5 years ago, and I think I've learnt my lesson.
So what actually is your research? What is it you're trying to find out?
We're researching lots of different aspects of climate change. John and I work on atmospheric science, so right from the kind of snow and what's happening at the snow-air interface up through the layer where we experience weather, and then the ozone layer, which I'm sure John will talk about above us, and then the upper atmosphere at the boundary to space. We research space weather. Antarctica is actually a great place to study things like the aurora. So all aspects of the atmosphere that form the kind of climate and the changes that are taking place that we're trying to understand at the minute.
We heard earlier about how atmospheric researchers here in Cambridge can deploy a network of sensors. They strapped a lamppost, which again is not an option for you, and now they are developing new technologies on these unmanned aerial vehicles that will allow them just to go up through the air column and measure everything. It can't be that simple for you. How do you actually measure that full column of air?
We've got a whole array of different instruments. We measure the upper atmosphere with big radars. So we often build masts and towers in Antarctica that can transmit strong radio signals up into the atmosphere and bounce them off various kind of sets of charged particles and things that can give us information about what's happening way up in the atmosphere. It was interesting hearing what they were saying, because one thing that we did one time when I was in Antarctica was fly unmanned aircraft, because we wanted to find out what was happening over the frozen sea ice in the wintertime when it wasn't safe to go out there as people. It was dark and it was freezing cold. Although we actually had some problems flying things by remote control because we were limited by the thumb freezing time, which depended on the temperature. We had a graph.
Sounds pretty painful.
It does.
Ouch.
So do these limitations as well mean that it's very hard for you to collect a full sort of year-round data set, or are you able to leave sensors there and collect data all year without actually having to go out into dangerous conditions?
We do have year-round data about lots of different places in the atmosphere there. I mean, some of it we collect, we're involved in the collection. A lot of it, we now have automated instruments that are collecting them, and they just need scientists and engineers to be able to fix them, because nothing in Antarctica works smoothly. There's always problems and challenges no matter what you do.
And Jonathan, if we could bring you in here, what sorts of things are you actually finding out?
I think one of the differences between, say, the UK and Antarctica is the density of the network. So typically weather stations in this country might be 50 kilometres apart, maybe a little bit more than that, often much less, 10 kilometres. In the Antarctic, we're lucky if we've got them several hundred kilometres apart. So that means that each station is much more valuable in itself in identifying what's going on. And we're looking at things on a variety of timescales. So we're looking at the climate as it changes over the ice ages in the really long timescales by looking at the ice itself. On the more historic timescale, we're looking at the slow change of climate in the measured period. So Halley was first occupied in 1956. So we've got 60-odd years worth of data from there. And intriguingly, the temperature, the mean average temperature at Halley, has not changed significantly in that period. And that contrasts with what's going on in the Antarctic Peninsula, the bit that sticks up towards South America, which is warmed by 3 degrees at the same time. And I have to say, why? What's going on? The answer is the ozone hole is what's going on. And it's quite fascinating that we're discovering that there are lots of indirect links between the climate and the ozone hole and climate. And one of the worries is that the ozone hole really tells us about how fragile our atmosphere is. It came from virtually nothing to full-blown in a little over a decade. We're now finding that it's affecting the oceans around Antarctica. And what's happening is that the formation of that ozone hole each spring is changing the wind system lower down in the atmosphere, which is then changing the ocean currents because the strength of the winds has changed. And we know at least in 1 or 2 places of Antarctica, that's then pushing warm water towards the Antarctic coast and is actually starting to melt from below some of the ice shelves. So it's a fascinating chain that links the two together. And of course, with the changing climate at the surface due to the increasing amount of carbon dioxide and methane in the atmosphere, although that's warming the surface of the Earth, higher up it's getting colder. And because the ozone hole forms because of the unique circumstances over Antarctica, we get a long period of really cold temperatures during the Antarctic winter, which allow clouds to form inside the ozone layer itself. And then the sun comes back in the spring, it illuminates those clouds, and on the surface of those clouds, chemical reactions have taken place that convert chlorine and other substances from things like freons and other halocarbons into an active form. You then get photochemistry, which destroys the ozone, creates the ozone hole.
It's a self-perpetuating problem, really. Once you have an ozone hole in the first place, the chemistry then will keep that hole going.
It will. However, one of the things that we globally have done about it is that all the member states of the United Nations have signed up to what's called the Montreal Protocol. And this is a tremendously successful treaty. It's working. The amount of those ozone-destroying substances in the atmosphere is going down, and it's quite clear that they're going down. But they'll be with us, or the ozone hole is likely to be with us for maybe another 50 or 60 years, just because these chemicals are so stable.
Is the hole shrinking, though?
Yes, I think it is. It's still quite early days, but it is quite obvious in our averaging data from Halley that we're seeing a recovery. When you look at the lowest level of ozone that's seen each year, it's rather less clear-cut. There's definitely a sign that things are improving, but we're within the noise level still. And also, that relies on there being no other external forcings. And you could still get the perfect storm, as it were, where the atmosphere conspires in just the right way to give you exceptionally cold conditions, exceptionally stable atmosphere. Combine that with a very big southern hemisphere volcanic eruption that puts extra particles up into the ozone layer, and we could get the worst ozone hole ever. But within 5 or 10 years, I think that will be past. We'll have had the worst ever ozone hole, and we can clearly say that through combined action, we have cured at least one of the environmental problems that are facing us.
That's incredibly positive news, of course. We have been talking throughout the whole show about how different and special Antarctica actually is. Can we learn lessons from the research that we do down there about the climate systems for the rest of the world?
Yes, because what goes on at the poles very clearly influences a much wider region. So there's quite good evidence that because the ozone hole is changing the wind systems, that's changing rainfall patterns and potentially affecting Australia. So that's getting quite a long way north. And so the other side of it is if we change how the oceans are being heated, then the ocean transport system, which brings warm water from the equator northwards and southwards. If we start tinkering with that pump, then we can have global effects on the climate.
Fantastic. And you know you're talking about somewhere special when you're describing Australia as quite a long way north. Thank you ever so much, Tamsin Gray and Jonathan Shanklin, both from the British Antarctic Survey.
And to finish us up this week, Hannah Critchlow has been immersing herself in the wet stuff with our question of the week.
This week, we're plunging headfirst into people problems. Ian from the wet Welsh valleys got in touch with this.
I'm curious about the amount of water on our planet. If we and all other animals consist mostly of water, does this mean that as animal populations increase, the amount of water on the planet has to decrease to compensate? Would love to hear your comments.
So, since humans are mostly made up of the wet stuff and the population is increasing, will Earth's water supplies diminish? Phil Robinson from the Royal Society of Chemistry had this to say on the subject.
The simple answer is yes. The Earth is effectively a closed system, and the total amount of water it contains is essentially constant. Now, some of that water is stored in humans temporarily while they're alive, and so the more humans there are, then the greater the volume of water that will be stored in that reservoir. Now, on average, a human will hold about 40 litres of water, and if we take the world's population as a round sort of 7 billion, that gives a total volume of about 280 billion litres held in humans, which is a lot. It's almost 1/3 of a cubic kilometre.
Oh dear. Well, since the world population is estimated to have increased by 3 billion in the last 50 years and is anticipated to continue to rise, should we all be sensationally stockpiling personal supplies of water in preparation for disaster? Fear not. Phil has more on the topic.
However, the total volume of water that exists on the whole of the Earth, in whatever form, liquid, solid, gas or biological, is actually about 1.4 billion cubic kilometres. So the volume represented by people is just a tiny fraction. It's not even a billionth of the total amount of water. In fact, to make it a billionth, we'd have to increase the world's population about 5 times. So in short, yes, humans are a reservoir for the world's water, but the amount of water that represents is really just a drop in the ocean.
So yes, Ian, you are perfectly right. Increasing human populations will decrease the amount of water left on Earth, but not by any significant amount. We now jog along to gnaw on a rather fatty question.
Hi, this is Magnus from Edinburgh. I've just heard of this thing called shrink violet wraps, which are apparently some way that women are now using to lose a lot of weight and fat off themselves. And it seems to be very effective, and that kind of instantly worries me. They apparently kill fat cells through lysis. It just sounds dangerous to me. Could you guys illuminate that area? Thank you very much. I love the show.
So, have you heard of this new anti-fat fad called Shrink Violet Wrap? Have you tried it? Does it work? And if so, how? Let us know your views. You can post on our Naked Scientists Facebook page. You can tweet at Naked Scientists. You can email Chris at thenakedscientists.com, or you can join in the live debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow will be wrapping herself in cling film all around the office this week just to find out the answer. I'm just kidding. That's it for this week. Thank you very much to our guests, Elizabeth Bilsland, Peter Ayres, Carl Toplin, Tamsin Gray and Jonathan Shanklin. Thank you also to Ben Vousler for joining me. The production this week was by Kate Lamble. Next time we'll be dining out on the science of food security. We'll hear why scientists are worried that we're all destined to go hungry in future, how the humble fly could hold the key to turning what we currently throw away back into nutritious food in the form of fish, and we talk to a researcher who's using genetics to make plants more energy efficient. The Naked Scientists comes to you from Cambridge University. It's supported by the Wellcome Trust and the EPSRC. I'm Chris Smith, and thank you for listening. Goodbye.